Since 1970, this red line is nuclear electric power. Those are nuclear reactors that generate electricity for the grid. And this is from nuclear energy. That's energy from within an atom. Talked about it before. When you break open an atom, you can do this and access a lot of energy. If it happens all at once, that's a nuclear bomb. But if you control the reaction and release the energy slowly over time, you have a nuclear reactor that releases heat slowly over time and can use that heat to generate electricity for the grid. That's a nuclear reactor. So this is nuclear electric power, and it rose steadily since the 1970s. It had to happen after first discovering that you could split an atom in the first place. That happened right around World War II. And this is, since the 70s, rose in the United States. Then it started to level off. We'll look at the reasons why things start to level off, and now we have the green renewable energies taking off, which is good, but nuclear electric power does have some controversy. And you might even have some opinions yourself, what you think about when you hear the term nuclear power, nuclear energy. This is what this would look like. We're going to look into the schematic of inside of a nuclear electric plant. And this is another thing that's controversial, that due to some accidents in the United States, all in the world, that led to deaths, that led to a lot of public anxiety. And so there's a lot of this, I don't want this in my backyard, not in my backyard, NIMBY. However, construction of nuclear reactors is about to take off primarily to meet electricity needs, and not necessarily in the US, but in Asia, in China in particular. They're building nuclear plants on the order of at least 100 that have been applied. So there have been nuclear reactor accidents throughout the history of nuclear reactors, and this is one of the larger ones. This was Chernobyl, 1986, and this was an accident that basically has led to no new nuclear reactors built in the US since the 90s, it led to a lot of public anxiety for good reason. There was a cover-up, it was a huge, lots of people were exposed to radiation when this meltdown happened. So accidents at nuclear power plants are real, they can happen, and this is something that is certainly, maybe not in my backyard, is realistic if accidents do happen, but on a day-to-day basis, in fact, a nuclear power plant is quite safe, and a well-running, working nuclear power plant is something I would not fear standing right next to this tower. Even though it looks kind of ominous, that white stuff, guess what that white stuff is? It's not smoke, it's not air pollution, it's just like what we've seen before with coal-fired power plants. It's water vapor. It's water vapor used to cool off the what's going on inside, which is a very hot reaction. That heat is used to boil water, and boiling water turns into steam that turns in a turbine that generates electricity. So this is cooling off that water on the back end. And so this is the bigger problem at nuclear reactors or nuclear electric power plants, is the nuclear waste that is stored on site. We don't currently have a place, no country actually has a plan to store its nuclear waste. So nuclear power has its pros and cons, but it does not emit greenhouse gases, no carbon dioxide emissions, there are no air pollutants, but there are these accidents and this issue of nuclear waste. There's also a concern of nuclear material that, if gotten into the wrong hands, can be used to make a nuclear bomb, which is releasing all the energy at once, in compared to a nuclear reactor, which releases energy slowly in a controlled manner and over time. Nuclear power is not necessarily called renewable, and it's not even always called sustainable, but it is definitely cleaner than fossil fuel sources. Nuclear power comes from nuclear energy, which is that last of the 5 major types of energy. It's energy from inside of an atom, and this nuclear energy is used to generate electricity for the grid. It requires breaking an atom open, And that doesn't happen during normal chemical reactions. Now, you're probably familiar with Albert Einstein and his equation, Einstein's equation, E equals mc squared. But all of these, you have seen all of these variables. This is E, that's energy. We calculated energy for electromagnetic radiation, that's energy in joules. And this is m for mass. And then this is c, the speed of light, with squared. So what this equation says is that when you take mass and you move it really, 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 really fast, which is actually not, in theory, you can't move anything faster than the speed of light. So this is the speed of light, c, the value for c, which is 3 times 10 to the 8th meters per second. That's the fastest, the possible speed that you can achieve in the universe. That's basically a speed limit, okay? So you can't actually achieve c squared. That would be 450 quadrillion miles per hour. It's only used in the calculation, this c squared. Mass inside of an atom is a very, very concentrated amount of energy. What happens in a nuclear reaction is not taking an atom and splitting it into a million pieces. What happens is actually taking an atom and splitting it into smaller chunks, and those smaller chunks are basically, you can take the mass that you start with and still have a mass that you end with that should add up to the original mass, but there's a tiny amount of mass that's lost, and that tiny amount of mass that's lost, when you put into this equation the missing mass and 0.1%, this multiplied by c squared, which is a huge number, will give you a huge amount of energy. And so this is due to what's called the nuclear fission reaction. So nuclear fission is starting with a very large atom. So this is showing a nucleus, which is just the protons and neutrons. And this is very large. There's a ton in there, okay? And so this is already unstable. All those protons don't really want to be packed in there. And it can easily be destabilized, and it's destabilized by bombardment with a neutron. So a neutron, remember, is a subatomic particle with mass but no charge. So something that's really large, easily destabilized, and what happens is it doesn't break apart into a million pieces. It breaks apart into 2 smaller atoms. Now these atoms are not the same as the original atom. So this actually does not obey the law of conservation of mass for a chemical reaction, because the atoms you have before are different from the atoms you have afterwards. You have mostly the mass is equal, but for the law of conservation of energy, what's interesting about this reaction is that energy is created from the mass, so that also breaks the law of conservation of energy. So in general, this equation saying that you can turn mass into energy kind of combines both the law of conservation of mass and energy and breaks both of them. Nuclear fission reaction, you get different atoms produced, and you can determine what those atoms are by how many protons there are, because the number of protons is the identity of the atom. So there will be 2 new different elements, 2 new different atoms produced from the original atom. And the other thing that's produced are more neutrons. So these 3 additional neutrons with the starting point of 1 will go on and start nuclear fission reactions. If there's more target nuclei around, there are 3 more reactions. So this is known as a chain reaction. So this is another version. This is the initial bombardment by a neutron of a uranium-235 atom. Okay, so this is showing this uranium that's all packed and it's unstable. This breaks apart into 2 new atoms, barium and krypton, and 3 neutrons. Those 3 neutrons then go on and bombard other uranium atoms, and this is going to continue on until all of the uranium in your sample has been reacted. Once it's started, moves on its own. It just happens on its own. This is a simulation of a chain reaction where each neutron starts its own reaction and produces more neutrons until all of those red atoms, the uranium, all of those have reacted. So how much energy is released is a lot. Even though there's a small amount of mass differential from before and after, the multiplying that by this very large value is going to give you a very large value for E. So just taking 1 kilogram of uranium-235, the mass difference, small amount, will give you about 22,000 tons of explosive TNT. So that's how when you release all this energy at once, you have a bomb. Or if you do this in a controlled manner, you have a nuclear reactor. And so what's shown here is this is the closest nuclear reactor to us in LA. This is San Onofre. It's down closer to San Diego, but you can see that it is, if you've ever driven down to San Diego, next to the 405, you have these two reactor domes, and it's right next to the ocean. That's on purpose, and we'll get to that explaining what goes on in a nuclear reactor, why it's usually right next to an ocean.